Happy Monday. So what I'd like to do today is start the unit on the removal of gaseous pollutants. What we'll look at today initially is we'll look at volatile organic chemicals, just a little refresher on these chemicals. I'm not going to go into any great detail about them. And then we will move through a number of options for controlling these pollutants. So first, just volatile organic chemicals. These are organic chemicals contain carbon. They're bonded to carbon and other carbon atoms, hydrogen, nitrogen, and sulfur. In theory, they do not include CO2, although many of the same processes that we're looking at here can be used to remove CO2. These chemicals volatilize at a significant rate. They include chemicals like benzene, which are toxic and carcinogenic. They include components of gasoline, naphthalene, and a whole host of other chemicals. Some of these participate in the formation of photochemical smog. We mentioned this, we've mentioned with methane, production of formaldehyde, ethane, and how hydrocarbons can react in the presence of NOx, where we have light and heat to produce ozone. So we've studied that in the past. Now we're looking at how do we remove and reduce the concentration of these hydrocarbons in the atmosphere in order to prevent photochemical smog. Number of sources include everything from solvent use. So for instance, trichloroethylene, tetrachloroethylene, tetrachloroethane, all used in dry cleaning, degreasing agents. We used Freon, which is a chlorofluorocarbon. We use solvents and paint thinners. VOCs are released during the transportation and storage of these chemicals, so including gasoline, can be produced from vehicle exhaust. In the petroleum and related industries, incomplete combustion results in the formation of hydrocarbons. Chemical processing and then waste disposal can release methane, also releases CO2. So how can we prevent these? We'll talk about the control in terms of prevention, in terms of concentration and recovery, and in terms of oxidation. So we'll look at these sequentially and initially focusing on pollution prevention. So one of the major aspects of pollution prevention is substitution. So for instance, we can use water-based paints, water-based coatings, inks, in place of solvent-based paints. Now this reduces the emissions of VOCs. It doesn't completely eliminate them because there are still solvents in water-based paints, and those solvents have to evaporate in order for the paint to harden. We can look at using less volatile or non-volatile solvents. For instance, pentane is extremely volatile. You can go to hexane, which is less volatile, heptane, which is less, octane, which is even less. So basically, as we increase the number of carbons in the carbon chain, that decreases the volatility. We can also look at replacing chemicals. So we can replace gasoline with compressed natural gas or propane, and that releases less hydrocarbons. One of the major substitutions was with tetraethyl lead, which we started using extensively in the 1920s as an anti-knocking agent in gasoline. We also used it in paints, released tons of it into the environment until the late 1970s when we started banning the use of tetraethyl lead. Sadly, the neurotoxic effects of tetraethyl lead were actually known in the 1920s when it was chosen as the anti-knocking agent. And that's a whole story in itself. But by about the late 1980s, we started looking at MTBE, methyl tertiary butyl ether, and only to find out that MTBE moves with the waterfront. So if you have a leaking underground storage tank containing gasoline that contains MTBE, that moves with the waterfront and actually can contaminate groundwater and drinking water supplies. So we no longer use MTBE. Now we're using ethanol. And MTBE was also added to try and control hydrocarbon emissions from combustion processes. Sad thing about this is actually back in the 1920s, they knew that ethanol was an anti-knocking agent. It was not chosen because it couldn't be patented, and there was a fear of the use of ethanol's impact on the petroleum industry and their profits. So it's quite a sad story. And we ended up, like I said, pretty much by the 1990s where we could have been in the 1920s. We can also look at process modification. So now we're looking at changing the process. So we can change the way we use rinse baths for electroplating operations. We can use public transport and carpooling instead of driving a vehicle. We can replace gasoline engines with electric cars. And we can use coating processes that do not rely on evaporation of solids. So for instance, UV lithography or fluidized bed powder coating. And then lastly, we can look at leakage control. And there's significant losses that occur when you're filling or emptying tanks. There are displacement and breathing losses. There are leaks through seals, so we can try and minimize those. So this image here shows a tanker truck filling an underground storage tank. One of the things to recognize is that as the tank empties, there's more and more headspace. So this is what we refer to as headspace. So if we have volatile chemicals, we'll refer to this as, we use octane or hectane, benzene. So let's just look at it as benzene. So we have benzene, and it volatilizes. So we have more and more volume available for that benzene to volatilize. Now, when we fill this tank, what happens to that headspace? It's going to decrease. Well, the problem is then, where does that vapor go? Well, as we're filling this tank, we're emptying the tanker truck. And as we empty, if we completely empty it, we'd end up with a vacuum. So what we can do is we take the vapors from the tank and we transport them, allow them to flow into the tanker truck. So we're collecting the vapors rather than allowing the vapors to be released to the atmosphere. And that's important because roughly 1.5 to 2% of gasoline is actually lost when moving from the producer to the consumer. And if you think about the number of vehicles on the road and the amount of gas that is produced, that's a significant mass of gas that is lost. And up to 40% of the hydrocarbons emitted by vehicles is actually due to evaporative losses. So if we can control these evaporative losses, we can significantly reduce the amount of hydrocarbons that are released to the atmosphere. There are other things we can do. We can also have floating roofs on tanks, and these are required for tanks above a certain volume. I'm not going to go into the details, but it's based on the vapor pressure of the chemicals in the tank and the volume of the tank. But these floating roofs can prevent and reduce leakages. The system here can recover about 95% of the vapor. About 5% is actually left in place to replace the volume lost as the gas is pumped. And then the other thing we can do is put vapor locks on the car to reduce the amount of volatile organics that are released while you're pumping gasoline. So these vapor locks can also reduce the evaporative losses by about 95%. We can also have seals. The first one is a typical seal that you have on a carbonated beverage. It is simply a thin wafer of an elastomeric material that's compressed, and that prevents, for instance, carbon dioxide from escaping from the bottle and keeps the soda carbonated. You can also have compression seals, and this is a compression seal, and this is the type of seal on a water faucet. So it has a screw turning mechanism, and that screws, for instance, on a faucet, the nut screws down over the body of the faucet that compresses this elastomeric seal, and that traps between the faucet and the stem of the valve, so it prevents leakages there. And this last one is a rotary seal. And this is it's actually a simplified illustration of the type of seal that surrounds the drive shaft of an automobile at the point where the drive shaft exits the transmission, which is filled with oil, and we need to prevent that oil from leaking out. So what happens here, and you can see this turn here, the elastomeric material is turned back on itself like the cuff of a sleeve. And then you're balancing tension there in order to prevent leakages with the desire for low friction and wear. But these are 3 different types of seals that we can use to try and prevent leaks. Any questions about seals and pollution prevention